So we start off pretty easy, difference of squares. Hopefully by now you already know what that definition is, and it says that, let me rewrite it so that we can discover it again together. So it says that if I have a squared minus b squared, if that is the setup, if you have a perfect square minus another perfect square, we can see that as a all to the squared minus b all to the square. Then we can factor that easily by saying a plus b and a minus b. Okay, so that becomes our definition. So let's look at some examples that I have over here, and let's see how we apply the difference of squares to that. So notice that it's always between two terms that are perfect with a minus sign in between them. So when I look at the first one, question 1, I'm seeing x all squared minus 6 all squared. So it matches our definition. So this is going to be x minus 6 and x plus 6. So that is it. It's all factored out. Let's look at number 2. So number 2, it says 4x to the fourth minus 81. Again, it's two terms with a minus, so I'm suspecting I can deploy the difference of squares technique. When I look at the first term, it looks like something perfect. It's coming out of 2x squared minus an 81 is coming out of 9 squared. So I end up with 2x minus 9, 2x plus 9. Well, we can do something a little bit crazy with what I have. I'm looking at the first term, which is 2x minus 9, and I'm claiming it's a perfect trinomial. It's a perfect square. I can write 2x as root 2x all squared minus 3 all squared. So if I break that down even further, I can get root 2x minus 3, root 2x plus 3, 2x plus 9. Okay. And I mean, you keep going on and on and on, but this level is okay. Okay. All right, let's look at the next question. So the next question is 2x squared minus 7. And my claim is that this is a difference of squares. We can look at 2x squared to be root 2x all squared minus 7 is the same as root 7 all squared. So by that setting, I can write this as root 2x minus root 7 and root 2x plus 7. All right. And then finally, we have question number 4, which is x squared plus 9. Well, this is not a difference of squares. It's a sum of squares. And we cannot factor. So this is not factorable. All right, we can only factor a difference of squares. So that's our first technique, factoring using the difference of squares technique. Okay, let's look at the next method that I have. So the next method I have is called the AC method, because if you look at your quadratic equation, it's always in the form ax squared plus bx plus c. And the way the AC method works is that you pick the plus c and you multiply it with the a, the leading term, and the leading coefficient, that gives you the product A times C. And your job is to find two numbers that when you multiply gives you the A times C, but when you add will give you the middle coefficient. All right, so let's see how that works. So when I look at the first example, I have A in that problem set is 1, B is 5, and C is 6. So when I take the AC, I get 1 times 6, which is 6. So now I'm looking for two numbers. When I multiply, it would give me 6, but when I add them, it would give me the 5. So that seems to be 2 times 3, 2 times 3. So what happens is that now that I've discovered those two numbers, in place of writing the middle term, I'm going to split it up into 2x plus 3x plus 6. Well, I'm going to add the remaining things. So plus 6, and then I have x squared at the beginning. All right. So now I have turned a trinomial that's a polynomial with 3 terms into a 4-term polynomial. And we have a special way to solve a 4-term polynomial. The goal is to pick the first two and then pick the second two and try to factor to see if there are any common factors. So when I do that, I get, if I take the first box, I can pull out an x out. I'm left with x squared plus, not x squared, but x plus 2 plus 3, x plus 2. At this level, you do see that x plus 2 and x plus 2 on the other side are the common terms between those two expressions that you see. So I can pull that out. If I factor that out, I get x plus 2 and x plus what? 3. All right, so that's using the AC method. And this you could have done with doing bracket bracket. But the AC method is more methodological, and it's a process that won't fail you regardless if the leading coefficient is 1. Okay, so let's look at this next example. Again, A is 1, B is 7, and C is 18. When I pick my A and C, I get 1 times 18, which is 18. And if I look for those two special numbers, I'm looking for two numbers. When I multiply, gives me 18. But when I add them, I get 7. Okay. So if I put the two together, I have, what two numbers give me that? That would be 9 and -2, 9 and -2. So now I can take the middle term, which is 7x, and express it as two terms. So I have x squared plus 9x minus 2x minus 18. All right, and so I've turned the trinomial into a 4-term polynomial, and from there I'm going to pick the first two terms, and then I'm going to pick the next two terms. and I'm going to try and factor to see if I can get any common factors between those two boxes. So the first box, I can factor out an x out. I have x plus 9. And then the second one, I can factor out a minus 2. So I'm left again with x plus what? X plus 9. Now, at this stage, you could clearly see there's a common factor of x plus 9 in both terms. So I'm going to pull that out again so that I'm left with, if I factor the x plus 9 out, I'm left with what? X minus 2. Okay. All right, let's look at the next example. So the next example, my leading coefficient A is no longer 1 but 2. B is minus 7 and C is minus 4. So I'm going to use the same AC method. I have 2 times negative 4 is negative 8. So I'm looking for two numbers that when I multiply would give me negative 8. But when I add them, I get negative 7. Well, those two numbers are negative 8 and 1, negative 8 and 1. So in place of negative 7x, I'm going to rewrite that using these two factors that I just found. So I have my 2x squared, then I have my minus 8x plus x, and then conclude that with minus 4. So again, I'm going to take the first two, and then I'm going to take the next two. Notice that I'm always including the sign when I try to get the next box, all right, so that I can capture the right sign, so that when I factor, things work out correctly. If you don't include a sign, chances are you might not get the next step to have a common factor, okay? So I see I can pull out a 2x, and I'm left with, gotta use black. So if I pull out a 2x, I'm left with x minus 4. And I can pull out a plus 1. I'm left with x minus 4. So I end up with 2x plus 1, x minus 4. All right. So, like I said earlier, the AC method works for both when A is 1 and when A is not 1. It works out because it's a step-by-step process. So you are not sitting down and kind of guessing how you do it, all right, using the try and error method. I like the try and error method, but this gives me some sanity when I'm trying to do factoring this way, okay? Most of you have also seen factoring in other forms. There are different ways of doing it. I've seen where they partition the rectangle into 4 pieces and they try to figure out where everything goes. I've seen the cross, where you try to fill in all the different pieces and try to figure out what is going on. All those are fairly good techniques to use. I'm just picking one of them to use, okay? Now let's look at the last one. So the last one is a little bit different because C isn't just a number. It's got numbers with variables, but we treat it the same way, all right? It looks quadratic, a little bit disguised, but that's okay. So my A is 1, my B is negative 5, and my C is 4. So if I pick my AC, I get 1 times 4, which is 4. When I pick two numbers, that would give me 4. And when I add those same two numbers, I get negative 5. That looks like 4, negative 4 times negative 1, negative 4, negative 1. So I have Well, with these two factors that I have found, that's going to replace the middle term. So I end up with x to the fourth minus minus 4 x squared y squared minus x squared y squared plus 4y to the fourth. I can factor an x squared out. I'm left with x squared minus 4y squared. I could pull out a negative y squared. I got x squared minus 4y squared. Now if I factor what is common, I get x squared minus y squared, and then x squared minus 4y squared. So I've factored it out, but one of the things about factoring is that you always have to make sure that it's completely factored. So by re-examining what I have now, I can see that the first factored form is a difference of squares. And then the second factored form also seems like a difference of squares. So I can keep factoring, all right? The first one becomes x plus y, x minus y, and then the second one becomes x minus 2y, and x plus 2y. So now they are fully factored, and it looks interesting the way things turned out, that we had an embedded difference of squares in the trinomial that was given at the very beginning.